Alright, chapter 9 is about rotational dynamics. So basically, we take what we learned from the previous chapter and we're going to, well, we already were applying it, but we're going to apply it to more situations. There's a better way of phrasing that. So, first off, we start with a new concept of torque. And just to kind of give you an example, if you are to open a door, um, let's say you're coming out of Quick Trip and it's one of the doors that don't have a handle on it. It is much easier to open the door further away from the hinge, like right where it meets contact with the door frame, than it is to say push in the middle of the door, or even worse if you push towards the hinge. Um, Even if you apply the same force, you're going to have different results. And that's kind of where force doesn't necessarily hold any physical meaning. So instead, we have something called torque. Torque is represented by a tau. This is a tau. Well, that's not a tau. That's something needs to be erased. This is a tau. It's a Greek letter, and generally tau will always stand for torque. Your book defines it as a force times the L is a lever arm. There are a lot of different terms for this, but I think your book sticks with lever arm, and I like it okay. Um, Torque is positive if counterclockwise, so that's why we decided which direction was positive or negative, and it's negative if it's clockwise. Now, this is important. The force must be perpendicular to the lever arm. Torque, the only way torque makes sense is if the force and the lever arm are completely perpendicular. And you know that it's never going to be like that. And so what you have to do is, in this situation, we have a force and it's applied. This right here, while not labeled, is your lever arm. This right here is going to be your pivot point. And so if you take your force and multiply by your lever arm, that wouldn't make any sense because it's not perpendicular. So what you need to do is take the component that is perpendicular to the lever arm, and that would be your F cos theta. And that would give you it perpendicular to the lever arm. And then you multiply that times L, although it doesn't quite look perpendicular. I probably didn't do a great job on that. We'll assume it's perpendicular, so there's that. And that's where you're going to spend most of your time is doing vector projection in order to figure out what your perpendicular force is to your lever arm. Or vice versa, you can find the lever arm that happens to be perpendicular to the force. Either way would work. So let's do a problem. Oh, wait. Your book likes to talk about center of gravity, and I put it in early. The center of gravity, you hear it talked about a lot, such as the Fosbury flop. I think it's called Fosbury. I'm kind of blanking right here. Basically, where as long as you have your center of mass above the bar for the high jump, you'll be able to clear the bar. And that's where we utilize center of gravity. For a rigid body, it's the point where the force of gravity we consider to act when we calculate the torque. And basically, you can find it using an equation very similar to the center of mass equation from chapter 7. The center of gravity is not always in an object. For example, take the St. Louis Arch. Your center of gravity is somewhere in between. So it doesn't always have to be embedded in an object to be the center of gravity. But one important note is an object will balance at the center of gravity. So if you have a meter stick, it's going to balance at the 50 centimeter mark, assuming it's uniform. If your meter stick is not uniform, you'll have to find the mark where it actually is going to balance itself. And so that's the key about the center of gravity. It will only balance when it's the center of gravity is at the pivot point or whatever you're trying to balance it on. So that's kind of a good way of knowing things. Now I promised a problem, and I changed this one and added a third part to it because I think it might help on one of your homework problems, but well, I guess we'll see. Basically, we assume, oh, here's our picture right here. It's like a gear shift that has three different forces acting on it, FA, FB, FC. And some are acting at angles, some are not. And we'll have to utilize that. But we assume that the distance from FA to the pivot point is 25. So FA is going to be 25. We assume, ugh, I didn't have a space here, sorry. FB to the pivot point is 18, and FC, in 19 centimeters to the pivot point for FC. The force of FA is 15, FB is 10, FC is 20. What's the resulting torque of each force, and what is the net torque? All right, so we'll have to find multiple torques here, so let's do that. First, let's find tau A. It is defined as force times the lever arm. And the lever arm is given as 25, but we don't know the force. So what we're going to have to do, going down here, is we find the force that's perpendicular to the lever arm. And so basically we have a miniature triangle right here where FA is now my hypotenuse. And so we need to find this side, and it's adjacent to my angle. So it's going to be FA cosine of 42. So I use that force instead. So I say FA, well, I'm going to write it out first, and I'll plug in numbers. How about that? FA cosine of 42. We know that FA was 15. Oh, forgot lever arm times L. Here we go. So 15 newtons cosine of 42 all times its lever arm, which I believe was 25 centimeters, which means I need to put that in meters. So 0.25 meters. Ah, that was a disaster. Okay, 15 times cosine 42 times 0.25. And that's going to give you 2 points. We'll just call it 2.8. All right, and the units for torque is a Newton meter. And just so you know, joule is also equal to a Newton meter. But this is not equal to a joule. Because a joule is a Newton meter in rotational terms times the radian angle that you go through. We have not covered that. We will, I think, later on in this chapter. But just so you know that torque is a Newton meter. Torque is also, if you look it up on a car, like it'll say toe weight, I think, and it'll say like foot pounds. Foot, length, pounds, force. And so, same thing with metric. It's Newton meters. But it is not a joule because it has to be, you have to take it through the angle of rotation in order to figure out its actual energy value. So keep that in mind, not a joule. And I'll erase that just because it'll make me feel better. Because that might confuse you. Probably shouldn't have done that. Maybe not. Okay. Joules, not joules, not joules. Anyways, let's do tau B. Oh, one other thing I need to do, I just completely forgot, is we have to see what direction it's going. And so if it rotates, it's going to rotate in this direction around our imaginary pivot point somewhere down here. And that's going to be clockwise, so I'm actually going to make that a negative 2.8. Should have done that earlier. But I needed to do that in the final problem to figure out the net torque. But, yeah. And I don't think I asked for magnitude, so I can't get away with just a positive. So I need to make sure it's negative. All right, tau B. I take the force of B, which was 15 newtons. And this one is already perpendicular. So I don't have to worry about projecting it. And I just need to multiply by its pivot point of 18. So I take 15 times 0.18, and I get 2.7 newtons. And once again, this one will have to rotate in a clockwise pattern. And so that's going to be a negative 2.7 Newton meters. Next up is tau c. Rolling down here, this one I made a little bit more complicated. So this is 64 degrees, but we really want to find is this angle right here. And so the complementary angle, 90 minus 64, is going to give you, what, 26? So really we should be using 26. Because we want to find this side of my triangle right here. And so this side is going to be FC cosine of 26. So I take my force, FC. What is FC? 20 newtons. Cosine of 26 times its lever arm, and I think I made it like a weird number. 19 is what I made it. That's kind of weird. It doesn't look like it's 19, but we'll go with it because I already wrote that down. I probably should have put like 26. Sorry. We'll just use the values that I gave you. Anyways, so that's going to be 20 times the cosine of 26 times 0.19. That's going to give me 3.4 Newton meters. And this is going to be positive because it's going to rotate counterclockwise around the pivot point. Because if I take that force and pull it down, it'll rotate in the counterclockwise manner. And so to figure out your net torque, just like we figure out our net force, we add them all together. So I take a negative 2.8 Newton meters, add that to a negative 2.7 Newton meters, add that to a positive 3.4 Newton meters. And I could do this in my head, but I've learned that I make mistakes sometimes when I do that. So I'm just going to put it in the calculator. So negative 2.8, negative 2.7, and plus the 3.4 is going to give me a negative 2.1 net force, net torque. Yeah. Okay, so what does the negative tell you? That means that the object will rotate clockwise. So the direction actually does really matter when you're doing torque, because if you have all these forces acting on an object and you want to know what direction it's going to rotate, that's why you need the convention of negative and positive. And if you're thinking, well, why couldn't we have just called counterclockwise negative and clockwise positive? They could have. Honestly, I don't even know when the convention started. I didn't even think about it until now. I don't recommend that because that'll confuse people, and that's not the standard, but it could easily be done just that way, and you'd have all the right answers. It just wouldn't be proper, rather. But you could still actually use it to, like, in applications in, like, the real world, strangely enough. But, yeah. Oh, I gave myself room and I didn't need it. Yay. Alright, so next up is rigid objects in equilibrium. A rigid body is in equilibrium if it has zero linear acceleration and zero angular acceleration. We talked about this earlier in chapter 4, maybe a little bit of 5, and that is that, remember, zero linear acceleration means it can be moving at a constant speed. Need to find my cursor here. So constant speed is okay. And same with zero angular acceleration. Basically, equilibrium applications are kind of balancing problems. Everything is perfectly balanced. Kind of like the tension problems that I gave you in chapter 4, where everything was balanced. Same thing when we deal with torque. Everything needs to be balanced. So, just like with the forces, the sum of all the externally applied forces is 0, and the net torque is also going to be 0. So the problem we did earlier was not equilibrium because the net torque had a non-zero value. But if it was 0, this would be an equilibrium problem. And so it's kind of just like a separate class of problems that we're going to do. So a classic problem is a seesaw. Here's a little seesaw of a child and a woman, and this actually makes a lot more sense this year. given COVID, strangely enough. But we have two children sitting on the ends of a 2.6 meter seesaw. One children has a massive, one child has a mass of 42 kilograms, while the other child has a mass of 38 kilograms. Their babysitter, she likes equilibrium problems. So where will she need to place her 6 kilogram backpack to balance out the seesaw? Okay, let's draw this picture out. All right. Oh, I'm going to use my super cool thing. Yeah. Bam. And let's do a bam. And let's do a bam. Okay, so anytime, remember when we have an object touching something, there is a normal force that's going to go up. And I can even use this cool feature to do normal force. And now I'm out of that, so I need to undo this. Okay, and then we know a few things. We know the whole thing is 2.6 meters. We know one child has a mass of 42, the other one has 38. So we assume they sit on the end of a seesaw because that's how it works. So I'm going to call this side M1. Ooh, that's bad. It's not really. There we go. M1G. And I'm going to call this side M2G. And then, okay, so we do know those two things. And I do know that the distance from here to here, because the whole thing's 2.6, it's going to be half of that. So that's going to be 1.3 meters. Not drawing the scale because it's not quite middle. And then there's going to be some unknown one that I'm just going to put dash because we don't know what it's going to be. And that's going to be the MB for mass of the backpack times G. Okay. This is where we need to use the fact that it's a equilibrium problem. And so the net torque on the whole thing must equal 0. When you set up a problem like this, you have to set up a pivot point. Any of these points could be a pivot point. Meaning, I could choose this as a pivot point. Yes, it's not pivoting there, but I could choose it. I could choose this point as a pivot point, or I can choose this one. Since there's a normal force and we want to get rid of it, we're going to choose this as our pivot point. And so I'll start off the first time actually calculating that torque of the normal force. And then after that, it'll just kind of be understood. So we take our normal force, Fn, and its distance from the axis of rotation that we're pivoting around. 0. They're going to be perpendicular because it's already at there, so it ends up being 0. So there's no torque at the point of rotation. So on a door, there's no torque at the hinge. Okay, the other ones are going to have torque. We will have M1G, and I'll leave some room, just in case I need to make it negative, times its lever arm, and I'll go ahead and write 1.3 meters. And so M1G, if it rotates around here, would go in a counterclockwise fashion, so that's going to be a positive value. M2G, just to go, since it's on the other side, is clearly going to be clockwise, so that one's going to be negative. So I'm going to subtract M2G times its lever arm of 1.3. Okay. And then we don't know, and we simply add it because it will come out to be the correct sign later on, but we simply add MBG, and we don't know its lever arms, so I'm just going to call it L for now because that's what we're actually solving for. All right, cleaning this up a bit, that's going to give me 0, because remember the net torque is 0. M1G. Doesn't matter who I call M1, but I'm going to start with the 42. Times 9.8 meters a second squared times 1.3 meters minus M2 was a 38 kilogram child. These are kind of big kids, I guess. Maybe not. Times 1.3 meter and times 9.8. Yeah, sorry. And then the mass of the backpack was 6 kilograms times 9.8, and I'm running out of room here, sorry, times L. Should have thought about that. L. There, you can totally see the L. All right, so basically, and I had to drop my units there. Your meters a second squared is going to cancel because everybody seems to have that. And your kilograms is going to cancel because everyone seems to have that. What they don't have all is meters, and so you end up with the unit of meters. It just works out. So, solve for L. Okay. Let's see here. Moving 38 times a 1.3 times a 9.8. And then I subtract my 42 times 9.8 times 1.3. Okay. And then I'm going to divide that by 6 and divide that by 9.8. And I get a negative 0.87. All right, so what does that mean? That means negative 0.87. This is the distance from the axis of rotation, or from the pivot point. We're going to say pivot point to keep consistent. And since it's negative, it'll have to be on the side of clockwise. And so, well, this is 1.3. That means the backpack's going to be, well, right where I put it. I did not mean that on purpose, but yeah, it's going to be somewhere in that region. And it should be on the negative side, because why wouldn't it be? This is 38 kilograms. This is 42 kilograms. Obviously, this kid is bigger, so this kid's going to win this seesaw balance if there's a challenge. So the backpack's going to have to be over here in order to unbalance him. But we can't just put the backpack on top of the kid because it's 6 kilograms, and that would be 44 to 42. And guess what? That's not going to balance either. And so that's why you have to put it closer to the central axis, and so that way it actually balances out. So, yeah. One other thing, I didn't use cosines or sines on this one because all the forces were perpendicular to the lever arm, so I didn't have to worry about that. It has to be about a ladder. It's just a classic. All right, I will come back and you'll find this in pretty much every textbook. I just got like 9 emails all of a sudden, so I bet it's a really good schnazzy problem, I suppose. Let's say you have a uniform ladder is pulled out to a point where it begins to slip. If this angle is 25 degrees with the ground, then what is the coefficient of friction? So, not a lot of information, I know. Let me draw a little wall here. Let's draw this picture out. There's a wall. And then here is a ladder. Oh, look at this go. Oh. Yep, see? Ladder. Not exactly equally spaced, I'm fully aware. But you get the picture. And then this, I need to make one for the ground. So, yeah, close enough. Alright. Undo that. Okay, so your first step is you got to draw out your force body diagram. Alright, well, we got a lot of things going on here. We will have a normal force exerted from the ground to the ladder, and I'm going to call this F and G. Normal force on the ground. Then static friction is going to come back. Yep, it hasn't gone away. And that is going to act to the left because the tendency of the ladder is to slide in this direction. And so static friction is going to push backwards to prevent it from falling. Then we have a normal force from the wall exerted right here as well. And then, of course, the weight of the ladder. Now, this is where the center of gravity comes into play. We assume that all of the mass is concentrated at the center since it's a uniform ladder. And so the weight of the ladder is going to go down, and I'm just going to call that W for the weight, at least for now. Technically, you could say that there is a frictional force up here but we generally disregard the wall frictional force in part of the classic problem. That requires a little bit more physics before you do that type of problem. But this would be your basic setup, having this information. What do we do? How do we process it? Well, normally we would say, okay, what's going on in the X, what's going on in the Y, back when we did, forces. So let's start with that. Let's start figuring out what goes on in the Y. Well, we've got the normal force of the ground minus the weight, and it's the moment just when it begins to slip, so it's an equilibrium application problem, so that's going to be equal to 0. That means the normal force due to the ground is equal to the weight of the ladder. Doesn't give me anything about an angle, coefficient of friction or anything about an angle. So that's about as far as I can go. All right, well, what about the horizontal, the X? All right, so going to the right, we have the normal force from the wall minus the static friction, and that's going to be equal to 0. And so the normal force from the wall is equal to static friction. Once again, that doesn't give me the coefficient of friction because we know that that's equal to mu SFN. And that actually would be mu SFNG, since that's the point of touching. And I do know that FNG is W, so I could make that substitution. So we would know that the normal force due to the wall is equal to mu SW. Still not enough information to solve this problem. Hopefully I gave myself room. No. Alright, I'll fit it in. It'll be fine. Okay, so that didn't work out. Now, since those two things don't work out, you try your third option now, which is torque. So you're going to pick the point to pivot around that's going to have the most forces cancel, and we will choose this point right here. This inner angle right here is 25. That's already given, so that's good. And so what I need to do is then torque it around this point. If we torque it around that point, I lost my cursor, that means the torque of F and G and the torque of the static friction will both be equal to 0. And so I only really have two torques. So let's do that. So it's a static equilibrium problem. So the net torque is equal to 0. And let's start with the weight. Okay, well, you're thinking to yourself, how am I going to do this if I don't have the actual length of the ladder? Because, torque is force times a lever arm. Well, this is what we'll do. We will call the entire length of the lever arm L. That means that this little portion is going to be L over 2, because since the weight acts at the center of gravity. I'll just leave it as is. Okay, well that gives me a little bit of help. So, okay, how should I proceed? Okay, let's do that. We know that torque is force times lever arm. Weight is a force, so I just simply called it weight for now. So W. The lever arm is going to be this side right here of the triangle. So that little chunk right there. And so what I have to do is I have to project now my lever arm, L over 2, to this side. And that will be, since it's adjacent to L over 2, that's going to be L over 2 cosine theta. So L over 2 cosine, and we'll keep it at 25 for now. All right. Now, what direction does that rotate? If it was allowed to freely fall, it would rotate in a counterclockwise position, so it should be a positive. Yay. All right, FNW is over here, so I'll take that one. And its lever arm, FNW, let me try to find my cursor here. There it is over here. FNW is way up here. And so we need the lever arm that is perpendicular to FNW, and this is always throws people off. But we need this side, which I'll just call y. Okay? We need that side. So that'll be all of L. It's on the opposite side, so that's going to be all of L sine theta, or sine 25. So go back over here, and I have L sine 25. Okay. That's a little bit better. Oh, one last thing is I need to determine direction. I tried to leave myself room, but I guess I didn't do a good job of that. So this one should rotate in a clockwise fashion if the force is allowed to rotate around this pivot. And so this should actually be a negative. I was going to put plus a negative, but I ran out of room. So I'm going to move that to the other side here. FNW L sine 25 equals W L over 2 cosine 25. All right, I can cancel some things. What can I cancel? L's. We didn't even know the length of our ladder. Oh, good, because I didn't know what I was going to do without the length of the ladder. I don't think I was going to solve the problem. So, yay. L's go away. Woo! Okay, so that helps. What else can I do? I do know that FNW, coming up here, is equal to mu SW, and I do need the coefficient of static friction, so let's make that substitution. Mu sub SW sine of 25 equals W cosine of 25. Ha! Weight goes away. Didn't have that either. Didn't know what I was going to do without it, but it's okay. It's gone away. Now all I have left is one thing, mu s. And so move my sign to the other side, and that gives me mu s is equal to the cosine over sine. It's going to be the cotangent of 25, or I always write this as 1 over the tangent of 25. Because cotangents, at least not on my calculator. So let's figure out what that is. All right, 1 divided by the tangent of 25, closing parentheses, gives me 2.14. 2.14 is quite high, but that angle is also pretty extreme. 25 degrees would be a ladder, actually, that would look like this. So it would have to be an ungodly high number, which is 2.14. Probably should have chosen a different angle, but that's what I got. Okay, so Newton's second law for rotational motion about a fixed axis basically put things swing differently, meaning it is much, if you have like a pen that you're holding right now, it is easy to twirl the pen by putting it in between your fingers in the middle of the pen and then rotating it back and forth, as opposed to rotating on the end of the pen, which means there's more weight, or rather it feels like there's more weight. There's not more weight, obviously, because the pen didn't change mass. What is changing is the way it rotates and the axis of rotation. And so that leads us to something called inertia, or rather rotational inertia. Inertia is indicative of mass and shows you how things will move in a linear fashion, whereas rotational inertia is indicative of rotational movement and shows you how you move in a circle. And so a good example of that is softball, which I've never played before, but maybe some of you have. You have a swing weight and an actual weight. The swing weight is actually based off of the rotational inertia, of basically how the mass is distributed throughout the bat. There is a proof to come up with this, and I shall show you how it comes. We know that tau is equal to force times the lever arm, assuming that they're both perpendicular. And we also know that force is nothing more than mass times acceleration times said lever arm. Okay, well, where does that leave me? A couple things here. Recall that since we're wanting to basically get some sort of rotational formula, I do know that A, the linear acceleration, is alpha times r. But if I had, let's say, a baseball bat, that's a terrible baseball bat. That is absolutely too terrible for me to even put down. That's better. And let's say that baseball bat is rotating about its end with radius L. I could say, instead of saying alpha R, I could say alpha L. Um, and then I can make that substitution. All right. Well, the L's will go together. To make ml squared. And then this is alpha. And then this right here is normally mr squared, is generally what it's regarding, but we're using L because of the the original proof. But this is called I. That's not good. There we go. Erase that there. Close enough. So this is defined, roughly defined, as mr squared, where I is your rotational inertia. And so this then relates in our final equation is tau is equal to I alpha. So I is the rotational inertia. It's basically how the weight is distributed. For a point particle, it is equal to mr squared L squared, whatever the distance from your radius is, i.e. for your rotation. It is not always mr squared for everything. Depending on the object, it has different rotational inertias. How so? Well, that involves calculus, and is kind of beyond the scope of this class. But there are ways of proving some of those. There's a little bit in physics 314 and 313 that you do, but really you have to take some far more advanced physics classes before you start proving all of the rotational inertias. And what are some of those? I should have that. Thought I had that on the last slide. Oh, I'm going to roll down here real fast. These are all ways or different ways of rotating. Not all of them, just some. And each of them gives their rotational inertia. So for a hoop or a cylindrical shell, it's just mr squared. You basically like a point particle. But for a hollow cylinder, it's 1/2 m. Then the difference between the two radii. Sorry, not the difference between the two radii, but the radii added together, the square of the radii added together. There we are. Solid disc cylinder. So this is your most common one that you're going to see is 1/2 mr squared. And in fact, if you don't really know what the rotational inertia is, you can just guess it's 1/2 mr squared. And most of the time it's going to be. And then some more odd ones like rectangular plates, thin long rod, either through its axis in the middle or through the end. So how it rotates right here with the long, thin rod will actually change its rotational inertia, which then will change how it actually rotates. And then solid and thin spherical shell also are a little bit different. So anyways, yeah, I jumped ahead a bit. But yeah, so rotational inertia is essentially something that you use to say how things are rotating. So, if you've ever read The Ballad of the Flexible Bullet by Stephen King, you would know what a forknet is, but if you haven't, most people haven't, that's fine. 300-gram forknet is standing on a uniform meter stick at the 20-centimeter mark, while something that is a displaced problem. Okay, that problem that was in between there, I'm not even sure what that was or where that was supposed to be, so you won't have it, so it won't really matter. But makes sense because this was supposed to be the next slide. I was surprised there was a problem in between there. And as I said before, basically all of these are found using calculus. For a point particle, you just need to know it's mr squared, and then for everything else, you can look up the actual rotational inertia. So let's do a problem on that. We have 4 3-kilogram particles are located 1.5 meters from each other and are rotating around the first particle located at the axis of rotation. So there's a 3-kilogram particle at the axis of rotation. There's another one located 1.5 meters away, and another one located 1.5 meters away. And so I do this problem because the rotational inertias of objects add up. So you're going to want to know the total rotational inertias I tot, and that's going to be I1 plus I2 plus I3, and this is 1, 2, and 3. Okay, well, what does that give me? So I1 is going to be the 3 kilograms. Actually, let's write it this way. I like this way better. We all know they're the same mass, so it's just going to be m r1 squared plus m2 r2 squared plus m3 r3 squared. I could pull out the mass to make this problem slightly easier. R1 squared plus R2 squared plus R3 squared. R1 squared, the distance between this particle, the number 1, and its axis of rotation is 0. So it goes away, just kind of like when we were talking about torque, how if it torqued at the pivot point, then there's no real torque there because there's no radius, no lever arm. We do have R2 and R3, though. So that's what I'm going to plug in next. The mass is 3 kilograms. R2 is going to be 1.5 meters squared plus R3, which will be 3 meters away. And so we take 1.5 squared, that should be 2.25 plus 9, times that by 3, gives me 33.75. And that'll be a kilogram meters squared. And that is your rotational inertia, your total rotational inertia. So the more particles that you have, the more rotational inertia you have. But notice it's also based off of the square of the distance. So that's why a thing like if something were to rotate and all the weight is put towards the far end from the axis of rotation, something similar to this, it'll be a lot harder to rotate it than if it were, I don't know, just like this. Because axis of rotation being here and here. Because it's further away and it's based off of that square of the distance. And some people call the rotational inertia rotational mass. It's not really a rotational mass, but you can kind of think of it that way. It is basically the inertia, or the mass that affects how it rotates, if you want to think of it that way, but it's not really truly like that. Alright, let's do one where we have to look up the rotational inertia, and I'll have to go back a few slides because I always do. Because I can never remember the difference between hollow, and I know the difference between hollow and solid, but I would never remember the numbers. So we have a 0.5 kilogram hollow soccer ball with a radius of 15 centimeters, has a tangential force of 10 newtons applied to the edge of the ball. What is the resulting angular acceleration of the ball? Like, whoa, that got bigger. Okay, well, remember I proved that tau was equal to I alpha? Right, that's why we needed to get a rotational inertia. Because if we want to find angular acceleration, we need to find rotational inertia. We also know that tau is equal to our force times our lever arm. So I could say that the force times the lever arm is equal to I alpha. So what's going on here is you have a circle, a ball, and it says there's a tangential force of 10 newtons applied. So this will be my 10 newton force. And it's applied around the center of the ball because you're making it spin, right? And then this right here is the radius of your ball. Okay? All right, good. So I'm looking for alpha, so I should go ahead and solve this for alpha. So that's FL over I equals alpha. And, okay, what is force? Force is 10 newtons. What is the lever arm? That's the radius. Careful, it's in centimeters, so 0.15 meters. All over I. Don't know what I is. So I'm going to go up here. And then it says hollow, so that's a thin spherical shell. And that's going to be 2/3 mr squared. Mass is 0.5 r squared, so 0.15 meters squared. This will cancel at least one of those, so that kind of makes it a little bit simpler. All right, so I'll take 10, divide that by 2/3, divide that by 0.5, divide that by 0.15. And I get 200 radians per second. Yay. Sorry, radians per second squared. I see what you're saying. All right, yeah, radians per second squared. So this is a way that we can use the Newton's rotational law to calculate angular acceleration based off of a force on the edge of a ball, or there's all sorts of scenarios we can do with this. But this is the key reason why we need rotational inertia, because otherwise we would not know the angular acceleration of said ball. I promised this, and so here it is. I talked about how torque was a Newton meter, but not a joule. This is why. Work is equal to force times a distance. And if we're going in a circle, remember we called it an arc length, so we called it S. So Fs, where S is the circular distance traveled by the rotating object. But we also know that theta is equal to S over R, right here. And that's kind of how we defined it. So we say that work is then equal to force times the radius times theta. We know that force times the radius is basically the same thing as force times the lever arm, and we know that that is tau. So substituting it in, we get that work is equal to tau theta. And so technically the unit for, well, not technically, but if you were to work it out, you would get the unit of work in a circular motion as a Newton meter radian, where radius is the true unit, so we drop it off. But that's a big deal. That work in a circle has to be multiplied by the angle it goes through, because if you don't, then you won't actually know how much work was being done, because you don't know the angular displacement of the object. So, and we've talked about energy before, and I'll have to prove this one right here. But we know that the kinetic energy, we learned this in chapter 6, is 1/2 mv squared. We also have something called rotational energy, and I will show you how to get that one. How do we get that? Well, we know that kinetic is equal to 1/2 of mv squared. We know that velocity is equal to omega r. So 1/2 of m times omega r squared equals 1/2 m r squared omega squared. Remember, mr squared for a point particle is just I, and so we get 1/2 I omega squared is the kinetic energy of a rotating object. So this is your translational energy, meaning the energy of it moving forward and backwards, and this is the rotational energy. And then in some cases you also need to know the gravitational energy. So now an object can have up to 3 different energies: translational 1/2 mv squared, rotational 1/2 I omega squared, and gravitational mgh. And that's, remember, it can only have rotational energy if it's actually rotating. So like a wheel. The car itself only has translational kinetic energy. Doesn't have any rotational energy. The tires, like I'm seeing a car driving through campus right now, and I'm watching the tires rotate around, and I'm like, hey, you tires, you have both rotational kinetic energy and translational kinetic energy. Now I can't see the tires, I only see the car, and then it's back to just being translational kinetic energy. So when you rotate, it creates its own energy. And you kind of saw that with that picture at the very end of last chapter where the bottom of the tire was moving twice as fast as the top of the tire. And that was due to the kinetic energy. Rotational kinetic energy, sorry. Got distracted by that car. All right. Okay. This is kind of a classic problem. It's a doozy, but it's a fun one. We have a hoop and a cylinder of radius r and mass m are at rest at height h on an inclined plane of angle theta. A lot of crap I didn't give you numbers for. I know. Which one will roll to the ground first on the surface if they roll without slipping? So let's draw a pretty picture. All right, pretty picture, done. And so basically we have an object that's going to roll down said ramp. We know that the height of the ramp is going to be h. And we're trying to figure out which one's going to roll to the ground first. Okay, well, how do we do that? Well, we use conservation of kinetic energy. We have K and PE. It's going to start from rest, so it's only going to have potential energy at the top. And at the bottom, we have K and PE. We're only going to have kinetic because it's at the ground. It doesn't have any more gravitational potential energy. Let's say, okay, so that means that your initial potential energy, PE naught, must be equal to your final kinetic energy, KF. And the initial potential energy is mgh. And the final kinetic energy is no longer just 1/2 mv squared, but it's 1/2 mv squared plus 1/2 I omega squared. Because remember, this object is not only moving left and right, well, left and right down a ramp, but it's also rotating. And so I need to make that substitution there too. Okay, now here comes the fun part. Not a lot of information is given, so how are we going to figure out who hits the ground first? Well, we could set up a nice little ratio, and that's what we're going to do. So we're going to do the ratio of, let's do, what's the first one that comes? Hoop and a cylinder. So we'll go hoop over a cylinder. Okay, so this will be M, because they have the same mass, G, same height, H, over MGH. So right off the bat, that's going to cancel and just give me 1. So that's going to help a lot. And then on this side, we're going to have 1/2 of M. The velocities are different, so I have to put VH squared for the velocity of the hoop, plus 1/2 of I hoop. Remember, the masses might be the same, but not the rotational inertia, so it's IH. And then the omega H squared. And then that's over 1/2 of MV cylinder, so VC squared, plus 1/2 of IC omega C squared. Okay. Couple things I know. I of a hoop is equal to mr squared. It's kind of the same as a point particle. And I of a cylinder is going to be 1/2 mr squared. The radius is the same, recall, because I said it's the same r. So I'm going to make those substitutions now. And I think I can fit it in slightly right here. That's going to give me 1/2 mvh squared plus 1/2 of, this is going to be my hoop, so mr squared omega h squared over 1/2 mvc squared plus 1/2 of its rotational inertia, which is 1/2 again, mr squared omega c squared. So now notice that mass is common and cancels. So I never gave you mass, but we never needed it. All right, so let's rewrite this and make it a little cleaner. This is essentially just 1 over 1. Or I can just call it 1, I mean. And then up top, it's going to give me 1/2 of VH squared plus 1/2 of R squared omega H squared over 1/2 of VC squared plus 1/4, 1/2 of R squared omega C squared. Well, recall that omega is equal to the velocity divided by the radius, or omega r is equal to the velocity. And so I'm going to make that substitution now. That's going to give me 1/2 of VH squared plus 1/2 of R squared VH squared over R squared, substituting in V over R for omega. And then R's then cancel. Yay, we didn't have that anyways. That's going to make our life super simple. And then over 1/2 VC squared plus 1/4 of R squared VC squared over R squared. R squareds cancel. All right, so that just gives me 1/2 VH squared plus 1/2 VH squared. 1/2 plus 1/2 is 1. So VH squared. 1/2 VC squared plus 1/4, that's going to give me 3/4 VC squared. And recall, they're both equal to 1. So now I can set both the equations equal to each other. So that gives me VH squared is equal to 3/4 VC squared. Okay, or if I square root both sides, that's going to give me VH is equal to the square root of 3/2 times VC, and putting that in numerical form, because I honestly don't know off the top of my head what the square root of 3/2 is. So that's going to give me 0.87. So what does that mean? That means all things being equal, the velocity of the hoop is going to have 87% of the velocity of the cylinder at the bottom of the ramp, which means that since we have to take a fraction of VC to get VH, that means your velocity of your cylinder is going to be greater than the velocity of the hoop. And you could do this for any objects that are rotating. All things being equal, the cylinder is going to reach the ground first because its rotational inertia is different. That's the only little factor that's there. It's just its rotational inertia. And the fact that its rotational inertia is different, even though it has the same mass, is what causes it to hit the ground first, which I think is kind of cool. Yeah, I know. It's a long problem, and it's a bit of a doozy, but it's a fun one, in my opinion. So, yay. All right. Now we talk about momentum, specifically angular momentum. Before, we talked about the conservation of linear momentum, etc., etc. Well, there is momentum with respect to angular momentum, and that is described by L is equal to I omega. So just like we had that your instantaneous momentum, P, is equal to mv, now you have its rotational counterpart, I, and you have velocity's rotational counterpart, omega. So it looks very similar. Just like how you had 1/2 mv squared for translational energy and then 1/2 I omega squared for rotational energy, it's the same you're almost substituting in the angular counterparts. Just like how we did at the beginning of Chapter 8 with the equations. It just happens to work out that way quite nicely. Angular momentum is described by a capital L. Why? I'm not really sure. And it has some weird units. That is true. Um, what are the units you asked me? Well, we know that I is a kilogram meters squared, and then that one's a radians per second. And so you end up getting an actual kilogram meter squared per second. You forgot the G. There you go. Very strange unit. Extremely strange. Another way of expressing it, I don't see this as often. This is the preferred unit, but you can express this as, let me show you. I could take kilogram meter squared per second and then multiply the top and the bottom by seconds. And that'll give me a kilogram meter squared per second squared times a second. And if you recall, this is mass times velocity squared, and that's a unit of joules. And so you could call it a joule second. Not the most common unit. It's usually kilogram meter squared per second, but you could express it as joule second. I suppose there's not really wrong with it. But physically, it doesn't make a lot of sense. Not as much, in my opinion, as kilogram meter squared per second. Because that tells me the kilogram meter squared per second tells me the rotational inertia carried over a certain amount of time. That's energy and time, and that gets a little bit more complicated. But it is a true unit. And the principle of conservation of linear momentum also applies to angular momentum. And so basically, we can take the sum, and we're never going to do many in this class, but we can take the sum of all of your initial angular momentums and set them equal to the sum of all your final angular momentums. And that will give us we can use it to solve for all sorts of cool stuff. And that's what we're going to do next. All right, so let's do a problem, mixing some things up. Let's say you have a 167 gram salad. It's attached to one end of a 40 centimeter massless rod. Why would they do that? Well, apparently, here's a depressing picture of salad on a stick. It exists. I did not know that. And then I knew that, and then I did a problem on it. At least it looks like there's some bacon in there, I think. Isn't there bacon right there? I think there's bacon. Is that bacon? I think it's bacon right here, and right here. Well, that changes things. It's not as bad as I thought. It's still pretty depressing, but if there's bacon on it, it makes me a little bit happier. But anyways, let's say you have a salad on a stick, because you do. It's 167 grams, and it's attached to one end of a 40 centimeter massless rod. Not quite like that in the picture, but I'm taking some liberties. Massless rod means something. If it was a massful rod, we would actually have to calculate the rotational inertia of the rod as well. But since we called it massless, we don't have to factor that in. Most of the time, you're not going to have to factor a lot of that stuff in just because it's a little bit beyond the scope of the class. The rod rotates about a pivot point at the other end. It starts from rest and experiences a constant torque of 0.05 Newton meters. We want to know how long it takes to make complete 10 revolutions, the angular momentum after 10 seconds, 10 revolutions, and we want to show that tau is equal to delta theta over delta t. All right, let's do that. Okay, what do I know? So I know the mass of my salad. Where'd my cursor go? There it is. And we know our radius. And we also know our torque. And we're trying to figure out the time it takes to do complete 10 revolutions. Well, how am I going to do that? I need to get time. But first, I do know it starts from rest, so I know the initial angular velocity. So there is at least that. Well, what I need to do is find the angular acceleration, and I can do that by using tau. It's a really crappy tau. That's a better tau. Tau is equal to I alpha, because we know what the torque is, but we don't know alpha. We know what I is. It's just going to be, it says massless rod, and so we could treat it as a point particle. So that's just going to be mr squared times alpha, or tau over mr squared equals alpha. So let's do that. So this will be 0.05 Newton meters. The mass is 0.167 kilograms. The radius, I think, was 40 centimeters. It was. So 0.4 meters squared. Yay. Let's do some math. 0.05 divided by 0.167, divide that by 0.4 squared is going to give me 1.87 radians per second. Yeah, that looks... okay, that looks okay. Alpha is equal to 1 point... we're going to round it up to 1.9. All right, so now that I know alpha, I want to know the time it takes to do complete 10 revolutions. So I want to use the fact that theta is equal to omega naught t plus 1/2 of alpha t squared. And I do that because I know that my initial angular velocity is 0, so it makes it pretty easy. We know it takes 10 revolutions, but remember we can't use revolutions. We have to use radians. And so there are 2 pi radians in a revolution. So that's going to give me 62.8. So now I know theta, so I can plug that in. So I'm going to come down here. All right, so 62.8 radians is equal to 0 for the initial angular velocity, plus 1/2 of 1.9 radians per second squared, t squared. And so just need to solve for t. So I take okay. I'm going to take 62.8, divide that by 1/2, divide that by 1.9, and then I'm going to take the square root of that, and I get 8.1 seconds. So this is kind of an interesting problem. I mean, as long as you know the mass and the distance from the pivot point, and a couple other variables, you can figure out how long it's going to take an object to rotate. Granted, no one's going to rotate solid on a stick. Okay, well, apparently people made it. Maybe they are going to rotate solid on a stick. And if they wanted to, this is how they would do it. But I imagine there are other applications out there where you want to know how long it's going to take to rotate something. Now we want to know the angular momentum after 10 revolutions. We know that angular momentum, it's really technically little l is for the instantaneous momentum, so that's I omega. We don't know what omega is. But I do know that omega is equal to omega naught plus alpha t. And now that I know the time it takes to do 10 revolutions, I can plug that time in, and then we know that that is 0. So omega is equal to 1.9 radians per second squared times 8.1 seconds. So 1.9 times that number that's already in my calculator. So that gives me 15.4. So to figure out its angular momentum at that point, I take its mass, 0.1, sorry, let me write this out one more step. Remember, that's mr squared for the rotational inertia, and then omega, so that's going to be 0.167 kilograms. My radius was 0.4. Square the crap out of that radius, 15.4 radians per second. Okay, do that. 0.167 times 0.4 squared times 15.4 gives me 0.41. .41 kilograms meters squared per second, because you just take kilograms, meters squared, put it over seconds. Radian isn't a true unit. Ha. Okay. Last step is they want us to show that tau, or our torque, is equal to the change in angular momentum over time. All right, well, how do we do that? Well, let's start with the equation that we do know. We know that tau is equal to our force times our lever arm, which we'll just call r. Okay, that is one thing. And then I know that mass times acceleration is going to be my force. So I have that. And then I also know that A is going to be, let me write this out. Acceleration is going to be is alpha r. Linear acceleration is equal to your angular counterpart times the radius times r. And then that's going to give you, of course, mr squared times alpha. So I've got a little bit to work with, and we've kind of seen this already. But what is alpha, by the way? Well, it's nothing more than the change in the angular velocity over the change in time, right? Right. Okay, that changes a bit. And then we know mr squared is I. So that's going to give me I. And then that'll be delta omega over delta t. We know that your angular momentum was defined to be I omega, and this is I delta omega. So that means it must be the change in angular momentum is going to be I delta omega. And so that means now that we will have delta L over delta T is equal to the torque. So this is another useful thing. If you know the change of your angular momentum with respect to time, you can get torque. And so this is a way that torque and the change of angular momentum are directly related, which is kind of fun. Anywho. Classic problem. Spinning figure skater. Now this is going to use the conservation of angular momentum. She spins, she brings her arms in like the picture, and when she does this, she changes her gyro radius by a factor of 4. Basically, a gyro radius is kind of like if it were a point particle, where would the mass be concentrated? Like, what would be the center of gravity, kind of? Well, rotational center of gravity, kind of. Anyways, she's going to change it by a factor of 4, or you can even say she just changes her radius if you want. What is her new angular velocity in terms of her old? So not a lot of information here. Not a lot of information. And she has a funny look on her face, but that's because she just ate salad on a stick. And I'd have a funny look on my face if I'm eating salad on a stick. At least it's got bacon. And it really does help with the bacon. It really, really helps. All right, so we know that we will have the sum of all of our initial angular momentums is equal to sum of all of our final angular momentums. Okay, and so that's going to be I naught omega naught, because we have just one person, equals I f omega f, because we just have one acting body. Okay. Not a lot of information, but we assumed it's like treated like a point particle. So I can say m r naught squared for its I, omega naught, equals m r f squared for its I, omega f. Oh, yes, mass goes away. Didn't have it to begin with. I was in trouble. Okay, well, I'm doing a little bit better, and it wants to know her new angular momentum, i.e. her final angular velocity in terms of the initial. So I'm going to solve this for omega f. That gives me r naught squared over rf squared omega naught is equal to omega f. We know that it changes her radius by a factor of 4. So that means rf must be 1/4 of r naught. Because we change it by a factor of 4 because she brings her arms in. So I'm going to make that substitution. I'm going to say r naught squared over 1/4 rf quantity squared omega naught is then going to give me r naught squared over 1/16. Sorry, I see what you're saying. That needed to be an RO. r naught squared omega naught. R naught squared goes away. That's why we did this. So we're left with 1 divided by 1 over 16, which is just going to be 16. So that's going to give me 16 omega naught. This is, remember, still equal to omega f, is equal to omega f. So by bring her arms in, and you've seen this before on TV, they bring their arms in and they speed up. And this is a very, very probably unrealistic situation unless you're like, you've got like an incredible, like your NBA player that happens to do figure skating, because then you'd have a huge reach and you could bring your arms in. But for most people, it would be by this factor. But the point is, you speed up. And you speed up not because you changed your mass, but you speed up because you changed your rotational inertia. And by changing your rotational inertia, it changed how you were spinning, and it sped you up. Just like that. So, fun. And then another application for this is in planetary motion. You can use the conservation of angular momentum to figure out the speed of the planet as it rotates around the sun. A planet, doesn't really have to be our sun, etc. But let's take Mars. Mars is moving at around 25 kilometers a second at its aphelion, basically the furthest point away from the sun. And that's about 1.66 AUs. And if you recall, an AU is equal to 1.5 times 10 to the 11th meters. How fast are we moving at its perihelion? And so this is kind of the same setup. We've got the sum of all of our initial is equal to sum of our final angular momentums. And this will give me I naught omega naught is equal to IF omega F. Now, planets are circular, so you would think, oh man, we got to use the rotational inertia of a sphere. No, they're pretty much point particles at that distance, because they're treated to be so small that its rotational inertia is nearly negligent. And so it's just going to be mr squared. So that's going to be m r naught squared omega naught is equal to m r f squared omega f. So now our mass cancels out because we didn't have that. Notice that the values I gave you are linear velocities, and so I will have to make a substitution here. And that's my next step. So I'll say r naught squared. This is going to give me v naught over r naught equals rf squared. And this is going to give me vf over rf. And my phone is ringing. I don't know why. People don't call me. I don't have friends. Stop it, phone. Stop it. It's spam. It is spam. Dang it. Sorry. Okay. Now, notice that your R naught cancels and your RF cancels, and you're left with one of those. And so that's going to give you R naught V naught is equal to RF VF. So quite a pretty simple relationship right there, which is kind of fun. All right, so we should plug in what we have. A couple tricks here is since AU is going to cancel out, I could just use the values in AU. And we generally will express the speed of planets in kilometers a second, so I could just plug it in as kilometers a second. So I will do that. All right, R naught is 1.66 AU, 25 kilometers a second, and then 1.38 AU, VF, AU's go away. Because even if I put in the 1.5 times 10 to the 11th, notice that it would cancel on both sides. And so it's kind of makes my life a little bit easier, you know. So 1.66, and I'll multiply that by 25, and I'm going to divide that by 1.38, and we will get around 30.1 kilometers a second. And a quick check. At your perihelion, you should be moving faster, because remember, if this is the sun, the perihelion is when you're closest to it, and your object should speed up slightly. And indeed, our final velocity happens to be greater than the speed at its aphelion of 25 kilometers a second. Believe that is it on Chapter 9. We shall move on to Chapter 10 soon.